cost. So there could be also interesting application, but this is the paper. Of course, it is a site for you. Now it's there. Another system which is very nice is fiber optics. Basically, in a fiber optics, you use the Kerr effect to change locally the refractive index. And basically, what is happening is that you then use another light pulse, and the light pulse, given that it has to slow down when it's approached from behind your region of higher refractive index, it cannot penetrate from the back, which works like a white hole horizon. And if it is instead getting inside, it cannot escape from the front, which is act as a black hole horizon. So there has been claimed that to see analog radiation here, but they were debated by us, by Uru. It looks like more a dynamical Casimir effect where you have a moving boundary, basically. Just to see the beauty of this system is that sometimes we have concepts that are quite, difficult to picture in your mind or that are not present in nature, like white holes. And you can basically produce them, the qualitative picture, very easily. So if you have this is basically a sink. You have a water flowing from the tap. You see what is happening? You cannot penetrate because this is a region of supersonic flow. And here you can really see that this is the analog of a white hole. Actually, you can have a description. You can basically, they did an experiment with a viscous oil that was much more non-turbulent and so on. Here you see the MACONs. You see that this is a region where if you create a defect, if you go outside, there is no MACON. Inside, there is the MACON. So this is a region where the water is flowing out faster than the velocity of the gravity waves. So the gravity waves cannot penetrate that region. And this is basically the qualitative analog, because this is too turbulent to do any experiment, of a white hole, of an anti-fractal region, where both the expansion of a going and going to basics are positive. The system I've been most looking at is Bose-Einstein condensate. Bose-Einstein condensate have a decisive advantage with respect to the system I show you because they are very easily to control and they are quantum system intrinsically. And they are systems where you can do this Bogoliubov approximation where basically you express the operator, the create and destroy atoms in your system as a mean field. This is basically the expectation value on the ground state, which is the mostly populated one, the one of the condensation, plus excitation. And it's important to keep in mind that this object create and destroy atoms, but it's different from what you call phonons, the collective excitations. So you have a ground state that is the ground state for the phonons, the collective excitation of the condensate that in some regime gives basically like a superfluid, is inviscid and irrotational. So basically the acoustic derivation that I show you applied straightforwardly. But it's different from the vacuum for the atoms. Of course, that is an aggregate of atoms. So what you can do is that you do the Bogoliubov approximation. You insert, basically, you have an equation for the mean field, an equation for the excitation. Now, you see here, this is sometimes called the quantum acoustic representation, but actually what it is a Bogoliubov transformation. So what you do is that you take the excitation equation, you basically diagonalize the Hamiltonian, and what you get is that you get to a system which is basically describing the perturbation on acoustic flows. And so we are back to square one. If you neglect this term, which is called the quantum potential, which is coming basically from the interaction term in the original equation, you get basically an equation for the excitation, which is again as this object, the name is a quantum object, but still is a perturbation of the velocity potential that propagates in a curved geometry. Of course, if you don't neglect this term, you have basically to do an equal approximation to get anything that is do not work with the differential operator. What you get a modified dispersion relation. This is the famous Bogoliubov dispersion relation. And this is something testable. It's a laboratory everyday life for people doing BC. But what it's telling you? It's telling you that if you have basically wavelengths which are much smaller than this typical wave number, which is related to the so-called Dilley length, which is basically the scale of coherence of the condensate. If you have a very long wavelength, you are back to a relativistic dispersion relation with the speed of propagation being determined by the speed of sound. If instead you have short wavelength, you have basically this modified dispersion relation. Now, this can be for someone a curse because you say, well, it's not really analog of gravity. We live in a relativistic world. But some other people can tell you, no, but this is just showing you a possible UV completion. And now you can ask yourself, okay, I have a system where I can reproduce an acoustic vacuum. This is a quantum system, so I can talk about phonons, not just about sound waves. What happens when phonons propagate? I mean, if I have phonons on this background, do they okay radiate in spite of the fact that you have this not superluminal dispersion relation? The group velocity goes to infinity for very large scale. So this, if you basically, if you want, was the part that one of the reasons why, in a sense, before we tackled this question, let me say that this was, in a sense, for me at least, the channel in which we enter in quantum gravity phenomenology. With Ted and David, we were trying to see, for example, the robustness of the Urw effect with respect to modified dispersion relation. So we were at the blackboard in the common room, and we realized that if the Urw detector was going at late times, was going very fast, at some point it would start to Cherenkov radiate. And we couldn't understand exactly what was happening. Actually, it's obvious. If you have a field which is propagating slower than your detector, what is going to happen is that it's like having an electron moving in a medium where the speed of light is smaller than c. So at the end, you will have Cherenkov radiation, but this time in vacuum due to a modified dispersion relation. So this is how we got basically to quantum gravity phenomenology. We started checking all the possible ways to test this modified dispersion relation. And basically, we did it in a way that was more systematic. So we said, okay, let's take the standard model. And basically, let's build all the operators that you can build order by order that violate Lorentz invariance. Now, you can catalog in two ways. Lorentz invariant Lorentz breaking operator can be CPT even or CPT odd. There is an anti-CPT theorem by Greenberg, which was demonstrated more or less when we were around in Maryland, which basically tells you this, that you can have a Lorentz breaking term in your effective field theory, which is CPT even. And basically, you built systematically the dispersion relation. And you may say, how is it possible that you can test a dispersion relation where you think that in this case, the modification is not coming at the Illy length, but at the Planck scale? Well, the point is that imagine you have a threshold reaction. What are the terms you have to compare? You don't have to compare in the dispersion relation p squared with, I don't know, p to the fourth or over m Planck squared. You have to compare the mass term, which is the term that determines the threshold, to the Planck suppressed term. And then you see that if you do this, for example, for electrons, if n is equal to 3, instead of the previous dispersion relation, n would be 4. You need 10 TeV. 10 TeV is something that you can achieve in high energy astrophysics. So you have the window of opportunity to test. So in effective, it's the standard model extension, you can write systematically how the dispersion relation appear. Then you have several astrophysical tests, and then you get constraints, and then you can get a feedback. And this is basically the very idea about quantum gravity phenomenology for Lorentz violation. I want to give you just two examples. So one is time, you can do time of flight constraints because basically your velocity of your photons, for example, becomes energy dependent. And if they propagate on cosmological distance, you can accumulate delays between different colors. And so in a sense, you can cast constraint if you have a good reason to believe that they have to start at the same time. You have birefringence. What is happening is that if you have CPT odd Lorentz violation, basically you have Faraday rotation in vacuum. So if you have a linearly polarized light, but composed of different frequencies, basically they, over time, they will go at 90 degrees and you will lose polarization. If you see polarized light from astrophysical sources, you can cast a very effective constraint. And then there is the synchrotron. And this is one of the main results that we had when we were together here at Maryland, because we realized that, for example, if the coefficient of the Lorentz violation in the electron is negative, what you have is that basically your gamma factor is up and down. But given that the critical frequency emitted by electrons in the synchrotron radiation is basically dependent on this gamma factor, basically, as much energy you have for the electron, you cannot go beyond the given critical frequency. The synchrotron spectrum dies off very rapidly beyond the critical frequency. So if you see 100 MeV as in the spectrum as the maximum energy reached by the synchrotron spectrum, for example, of a source like the Crab Nebula, then you know that this object must have basically, you can constrain the coefficient of Lorentz violation in this way. And this is how we made our paper on Nature at the time. Later on, I came back to this issue because it wasn't constrained on the case of positive coefficient of Lorentz violation. In that case, your electron at some point will Cherenkov all their energy and will be exhausted very rapidly. So you can do truly a very consistent constraint. And then in addition, we get polarized light from the Crab Nebula. You can also use that, and you get a very severe constraint on Lorentz violation as mass dimension 5 operator CPT odd. Then you may say, okay, but these are not the operators that are generating the P to the fourth Bogoliubov light dispersion relation. For that, of course, you need to go to higher energy. There are the ultra energy cosmic rays. Alas, we don't understand very well the physics of ultra energy cosmic rays at 10 to the 20 electron volt, because at the moment they were supposed to be protons doing the GZK, a couple of basically interacting with the same bit of photons and decay. But basically now we think that they are heavy ions. It's a much more complicated physics. So the constraints, I wouldn't call them at the moment robust. It has been like this for more than 10 years. It's very frustrating. We will have to wait for the astrophysicists. Let me go back to annual gravity. So now the question was, okay, but I haven't modified dispersion relation. How this modify? Doesn't this modify the OK radiation? Is OK radiation robust with respect to ultraviolet physics? And why people was worried? Why, in particular, the two people that at the time were most, able to pinpoint this problem were Bill, Uru, and Ted. And the problem is the so-called Transplanckian problem. The problem is that basically you cannot boost away an S wave. So you have high frequency. The black hole, what it does is basically you have infrared stuff at infinity arriving at this thing, you trace it back, even in the free-falling frame, you get frequency that very rapidly become Transplanckian. So it seems that you need to have some assumption about the UV completion of your vacuum to draw a conclusion about but basically to believe the original Hawking calculation. Analog gravity served as a tool providing a concrete model where you know what is the UV completion and showing you that there is instead a robustness. Now we are convinced that OK radiation doesn't care at what happens at the Planck scale close to the horizon. And I will try to convince you about it. I mean, this is also, yes, this is the point that at that time in the 90s, this was one of the main reasons why people in gravity theory were looking at this system. So there are many ways to build a black hole. I just want to highlight that there was one done at the Technion experiment by Jeff Denauer, which was basically creating a Bose-Einstein condensate, a controlled waterfall of atoms. And basically they reach a sonic point and generate basically an horizon. Later on, you may ask, but how you see OK radiation of photons? Do you put a microphone in the PC and listen? No, you don't. The trick, what it is, that OK radiation is basically associated to a squeeze state. But now you're like God. You can measure particles, the Hawking partners, on both sides of the horizon. And you know that they must be correlated in a very special way. So this is a numerical simulation done by Jacopo Carusotti and collaborators in 2008, where you see 0 is the horizon, and this is basically inside and outside. And basically you have that there are correlation of the particles, these called mustache. Now, the definition is not so good, but this is the experiment. You see the same mustache, which are the correlation between the Hawking pairs. So the Hawking pairs are correlated exactly the way they should be. And also, there is in the experiment a regime where you see for a while a constant temperature. This temperature is exactly the surface gravity that you would calculate for your acoustic horizon divided by 2 pi. So nowadays, we are pretty much, there were a lot of check and balance. I mean, a lot of people was convinced that this was Paulstanius and me. I mean, there has been a long story that I'm cutting short, but mostly the consensus is that this experiment actually saw Hawking radiation. Yes?
Yeah, could you just say what the process is that's happening there? Like what's
Okay, there are two processes here. You see this, this one is the dynamical casing effect. They are generating dynamically in acoustic horizon. This is like a collapse.
Yeah.
So there is a burst of radiation, and these are the correlation of that is due basically to the fact that you have particle creation in a time-dependent space-time.
Okay.
But you see, once this goes away, you remain with this stable, I mean, this is loopy, but this would be a stable, this mustache are basically telling you that there is a correlation between a particle outside and a particle inside, which are the Hawking partners. This one is basically that on the diagonal there is an anti-correlation, but that is basically the background. It's not the signal. Yes?
Sorry if you already said that while I was dealing with the room, but is there any notion of black hole entropy in these setups? So can you like formulate some version of the information paradox and look at it?
Can I answer this at the end? Because it would be drawing. I mean, the answer is you can introduce a force entanglement entropy.
Yeah, but for the information paradox, you need something like the Bagestein-Hawking entropy, right?
Well, exactly. That is because if you have in mind the page curve, basically you want to have a notion of Boltzmann entropy and a notion of entanglement entropy. So that one per se is not there because the Bagestein-Hawking entropy is a gravitational entropy. But if you want, I can tell you more because there are still lessons you can learn from analog gravity also for that, but I didn't have time to speak about it today.
Thank you.
Okay, but how the robustness work? I mean, I just tell you that the experiment to see the Hawking radiation, but how it works, how it's possible? Because if you think about it, the Hawking quanta, when they get closer to the horizon, they are blue shifted, that the UV part of the dispersion relation should matter. So first, some facts, the results. The results is, okay, this is taken by a beautiful Scientific American paper that Ted brought with Reno Parentani, which was showing basically that depending on the sign here, you have that basically the trajectory of your rays, they look like the relativistic one until they get close to the acoustic horizon. But then if you are in the supraluminal case, you see them coming from inside. In the subluminal case, they are coming from outside. We will see that in a moment really graphically. But basically, what it comes out is that what it matters are few facts. One is that you need to have the analog of the Ur vacuum. So when you set up dynamically your acoustic horizon, starting from a flow at rest, basically you generate you bring your quantum state in the analog of, it would be the analog of what normally is called the in state, but you know that the in state at late times will look like the Uru state. So secondly, you need to have a separation of scale. So the surface gravity of your black hole needs to be very different from the scale of the UV physics. And this separation of scale that is basically protecting the effect. Also, there are a few strange stuff. The horizon is insensitive. Basically, if you put a small perturbation in the flow on very short length scale around the horizon, your surface gravity is insensitive to that. It's like it is becoming thick, the horizon. It's not a point-like horizon. And well, I think basically the same things. And the outcome in this case is that you have a temperature which is constant for very many wave numbers until you consider basically particles which are really high energy, then you start to have deviation from thermality. But how does it work? I mean, the problem is that these are complicated calculations. Most of what we had was basically numerical, for exception of an analytical calculation that I will discuss now. So can we get a better analytical grasp? Because another fact that is strange is that numerically foreseen that if you have an object, if you do a velocity profile that is very close to form an horizon, but has no horizon, you get a non-thermal radiation that smoothly goes as you tune the velocity profile to generate an acoustic horizon to Hawking radiation. That looks like there is a progenitor, a non-thermal progenitor of Hawking radiation if you have a subluminal dispersion relation. That means the minus here. And in addition, you have a flow that simulates an ultra-compact object, something very close to form an horizon, but not with an horizon. And that is something that you see numerically, but nobody was understanding really why that was the case. So let me try to set it up. So you see, this is the velocity profile. It's like an hyperbolic tangent. But normally, you see, the acoustic geometry can be cast in this way. It's like Schwarzschild geometry in Paleveguscan coordinate. And normally, we choose by V negative because it will be corresponding to the sign that you get when you have outgoing Paleveguscan. Paleveguscan is a kind of horizon penetrating coordinate adapted to free-falling observer. And basically, as Eddington thinks that there is an outgoing version and ingoing version, depending if you want to describe the region outside the black hole and the interior of the black hole, or the region outside the white hole and the interior of the white hole. So normally in acoustic works, in analog gravity works, we choose B to become negative. B equal -1 is the sonic horizon, and more negative than that, basically you get the supersonic region. Now, one thing that you can do is the first exploration can be done with the tunneling approach. So the tunneling approach is the very idea is that you can think of the two Hawking quanta, no? The Hawking partners stripping away at the horizon. And what you can do is that you can reverse, basically, instead of taking a negative killing frequency one, you take a positive killing frequency going backward in time and tunneling out. This is basically the idea. How you do that? You go in a WKB approximation, you introduce an action basically for your particle, and then with this action, you know that the K rate, the tunneling rate is basically the imaginary part of this action. This action is basically K of the radial component of your free momentum, and what you see is that in spherical symmetry. And this, what you see, is that it has a pole at the horizon. This is the relativistic calculation alla Paris-Wilch. And this pole corresponds exactly to have a tunneling rate, which is minus omega killing frequency over TH, where TH is exactly the Hawking temperature. Now, in our case, what you have a preferred frame, the frame in which you provided a dispersion relation, and you can basically take the force velocity of your fluid and the vector orthogonal to your force velocity. If this reminds you what Thomas was doing yesterday with Orava gravity, it is very close, although there are some difference that if you want, I can tell you at the end. And then you have a way to relate your killing frequency, which is the conserved frequency along the ray. We are in stationary flux. With the preferred frame quantity, and this is the simple relation that you get. Now you have your Klein-Gordon equation for your field with the Lorentz breaking term, and then you can go again a WKB approximation to get to the dispersion relation. The dispersion relation, depending on the sign of the psi, can be subluminal or superluminal. Now what you can do this. You can take the dispersion relation, and you see basically inserting omega, capital omega of little omega in the dispersion relation, you basically get rid of little omega of the energy in the preferred frame. And now you have an equation which is just an equation in K and capital omega, which is a constant, because for each ray is the conserved quantity along the trajectory. This allows you basically to do ray tracing. You can see what are the modes propagating in your spacetime. And this is what is happening. You have an infalling mode, which is always regular, goes all the way in. And you have, this is the subluminal dispersion relation, exactly what I said. Now, there are, if you trace back the Hawking quanta, they are coming from the past, from Scray minus, basically. While in the superluminal dispersion relation, they're coming from the black hole interior. Now, the velocity profile that we have there is no singularity. But note that if you try to export this to a black hole in general relativity, you will be worried. You will be worried because you may say, well, maybe that there are, I need to put a boundary condition at the singularity. This is something that Ted was discussing back then in, I think, 94. But these are the situation, okay? Now, what is important here is that there are 4 modes here. You say, why there are 4 modes? 1, 2, 3. But you see, this one is not the same mode. These are hard mode in the sense that they are of order lambda, the cutoff scale. Here they become approaching the horizon softer. And here there is a turning point where your duplicable approximation fades. And then you have 2 soft mode, which are basically, if you look out only from here above, they look like the Hawking pair. Now, however, here in principle, there is no pole. So the tunneling would give you nothing. However, you can do the following. You can realize the following thing. If you take the infalling mode and invert the group velocity of this infalling mode, which is everywhere regular, you find that you track, you basically get these regions of the 2 Hawking partners. That means from the infalling mode, changing the sign of the group velocity, you get the outgoing modes both inside and outside, far away from the horizon. And if you do an expansion, basically a truncated expansion of what they are doing, you see that they seem to be linger here. Here is very accentuated, but for low killing frequency, they do this. They linger close to the killing horizon very long, and then they move away. So what is happening here is that you do a kind of expansion, truncated, and it looks like they have a pole. But actually, then what you can do is the following. What we did is like, okay, let's try to say that kappa plus, the momentum of the outgoing mode, is related to kappa minus, the momentum of the ingoing mode. Actually, as kappa plus is minus kappa minus plus something. And then we calculated what is this something that basically generates this, reproduce this apparent lingering at an horizon. Okay. So what is happening? It's happening that these objects are not lingering at the killing horizon, but they're lingering slightly inside for a superluminal dispersion relation, which is obvious. If I take a relativistic dispersion relation with C greater than 1, the horizon will be inside the killing horizon. With C less than 1, it will be outside of the killing horizon, like in Einstein. I mean, in Einstein, it would be. So here, what is happening is that this trajectory that we call the approximant, which is basically a trajectory that maps the ingoing mode to the outgoing mode, both inside and outside. Actually, there is a difference of sign between outside and outside, but this is not so relevant. It takes this form. If you do all the calculation, you find, you see, if without this term, it will be just a reversing the group velocity because omega is the same asymptotically. For example, little omega and capital omega are constant. But here, you have this term which shows a pole where the group velocity of the infalling mode is equal to the velocity of the flow. Now, if you do basically you can calculate the surface gravity at this effective horizon, which is the horizon effectively introduced by the dispersion. You're taking into account that the dispersion moves the perceived horizon of the ray slightly inside. And then you need to calculate your action, and then you do the tunneling. What you get is you get a result like this. You have this logarithmic dependence that is going to give you again the temperature. But you see, there is a kappa effective. Why is not the kappa effective horizon, but a different kappa? Because when you have a dispersion relation, the momentum is not parallel to the tangent to the ray, because the dispersion relation creates a mismatch. And that generated another effect that has to be taken into account. So that can be rewritten in an effective surface gravity, here having the killing frequency. So at the end of the day, you do all the calculation, and this is what you get. The effective temperature felt by that you get basically by the tunneling is the killing temperature, the Hawking temperature. You see, there is a 1 here. Then there is a correction that is suppressed by omega killing over the cutoff scale. Now, in Hawking radiation, which is the leading order of omega killing. Most of the omega killing are at kappa. So if kappa is much smaller than lambda, this is a very tiny correction that explains the robustness. And you see there is an additional correction that we I think nobody had found before. This correction is basically telling you that you have also to take care that your surface gravity radially doesn't change too fast. It's an adiabatic condition radially that you want that. I mean, of course, if your velocity profile is a straight line across the acoustic horizon, then this contribution is exactly zero. But it's telling you the robustness where it's coming from, because it's showing you that the next correction is this. Yes, and in doing this, I just want to add that in reproducing this approximant, we had, what really the calculation tells us that the approximant is thick. The effective horizon is thick again. We had basically is thick, but the thickness is suppressed by a factor which is the momentum of the falling mode divided by lambda. So you have to go to the next order to see this thickness. Now, normally, this also explains why you see some effects also when you don't have an horizon, but you have a subluminal dispersion relation. Because you see, if you go sufficiently IK, for sufficiently IK, they are slow enough that they see an effective horizon, even if there is no horizon. So there is a four-mode, two-mode convention, even in this case, although at low energy, there is also a four-mode channel that will give you a lot of scattering and noise. But anyway, this explains part of the numerical result to show you why you get this kind of non-thermal contribution getting close to forming the horizon, because basically in a subluminal dispersion relation, you have this effective horizon start to appear before the killing horizon is there. And you can prove that effectively for them, for these modes, there are negative killing energy states inside the effective horizon, which is nice. Which is like to say that if you have a graph star, an ultra-compact object, and you have a subluminal dispersion relation, it may radiate. Which is, because there is no ergo region normally, the reasoning is stationary, there is no ergo region, it will not radiate. But you can show that for the modes, you need to be really close to have an horizon, otherwise the modes need to be above their lambda. But for the high energy modes, what is happening is that there is also a phase horizon. There are negative energy states available. So effectively, there is an ergo region there. So now, why the approximant works? The upshot is very simple. It's because basically I don't know if one of you is familiar with the concept of quantum atmosphere. Basically, if you look at when the quanta go on shell, they go on shell at a distance from the horizon, in which the approximant is already tracking very well, is starting to track very well the Hawking quanta. So it's basically they go on shell when they are separated by the Broglie wavelength, if you like, and if you check for omega killing much less than lambda, otherwise this is not true. For omega killing much less than lambda, so at low energy, this is happening sufficiently far away from the horizon, from which basically is already a very good approximation, which is what is also said in very many papers by Schutzer and Uru in a different language. Now, I just want to close that we recently did the same analysis following step-by-step the only analytical calculation present in the literature, which is by Parentani, Coutin, and Finazzi, and where they were doing basically scattering matrix not with in time, not between in and out, but basically interior, exterior. And here you need to have four modes in the stereo. I told you that there are two real modes in the stereo, but there is also a complex conjugate pair of the corresponding to a growing mode and a decaying mode. Parentani did the same analysis. So we basically follow step-by-step his analysis, just going to the next order, taking into account the shift of the killing horizon, the fact that the lingering is happening around the effective horizon. And if you do so, you will momentum space to do so, because there the WKB approximation always hold. And basically you do all the calculation and you get that it pulls out again kappa effective, exactly It's just going the next order in the Parentani calculation. We just wasted a lot of time trying to understand how they did the recruiter profile, which was a kind of magic. And then the end, you compute the spectrum, you get the Hawking spectrum, and I write to the closure. So to me, this is telling you several interesting things. First of all, it's showing you analytically in a very simple way why the Hawking radiation is robust. You really see how the temperature start to become energy dependent very late when you need the black hole to be, or the black hole to be very small, kappa to be over their lambda, to start having global can be dominated by killing frequency, which are so large to start having the correction being irrelevant. The same analysis we did can be done also for subluminal dispersion relation or dissipative dispersion relation. It doesn't matter what happens close to the horizon. They can become part of TED quantum Mach, but it doesn't matter because as long as basically that the approximant give you the region of the pole and it tracks the Hawking quanta always in the region where the Hawking quanta are becoming really a real particle. And basically, the approximation in the Bogoliubov calculation you have is that you have you need to assume that the ingoing mode is low energy, always low energy. You need to assume that an adiabatic condition that in momenta also kappa doesn't change too much. And you have to ignore the backscattering. Basically, like in Parentani, you ignore the fact that the ingoing mode can backscatter with the outgoing one. That would be giving you great body factor other correction. And finally, this basically tells you that there is a hierarchy. There is always an Orlik-like emission. If these approximations are holding, you can define an effective horizon and an almost constant temperature. And if you have that the dispersion relation is killed, the lambda goes to infinity, you recover basically Hawking radiation as we know it, with exactly from the same formula we have without redoing the calculation. Now, all of F becomes exact. The approximant that I have defined is exact in the relativistic limit. You can fully reconstruct the Hawking quanta from the ingoing mode. And the ingoing mode, yes, the approximant is exact in the relativistic limit. So if you give me the ingoing mode, this is regular everywhere, I can always map the ingoing mode in the outgoing mode with the approximant. And then all I need basically is I hold everything under control. If the vacuum state for the ingoing mode is regular, then I can reconstruct the trajectory of the Hawking quanta exactly. And that is telling you that basically it's just a mode conversion of the ingoing mode into the outgoing mode. And this is basically the thesis that was in this paper by Ted in 1996. To me, it's as close as you can get to embody the philosophy of that paper by Ted, which I think can be embodied by this motto that will be the motto of the conference. Okay, thank you.
Time for a couple questions.
This tunneling approach to Hawking radiation, I have to confess I've never understood it.
Right.
And the thing, to just point to one specific thing that bothers me, you have this pole and you get the Hawking result if you go like, if the contour goes around the pole in the right side, the correct side. Now in quantum field theory, the analyticity property is coming from a statement about the vacuum. What is the actual state of the field that's leading to Hawking radiation? And I don't see where in the tunneling calculation that information is imported to select the contour other than to just get the answer you want at the end. Is there a better way to justify?
There is a paper by Walter Moretti that tries to address exactly your question, and it shows much more rigorously why you need to take that contour. But I also have concern, this is why we did the calculation of Parentani, which is a Bogoliubov calculation to convince ourselves. The second calculation is basically exactly to get around this. So we just, the second calculation, we don't use any tunneling. In the last paper, basically, we show the tunneling again, but because moreover, we have forgotten. We overseen in the first paper that the fact that kappa covariant the momentum that enters in in producing the Killing frequency is not the tangent vector to the array. And this is something I should have known because it's well known if you work with bonafide dispersion relation. But apart from that, basically, then we did exactly like Renault, following step by step Renault, doing the same contour, checking everything. But with the only difference that now we have, we identify where the lingering happens, which is not at the Killing horizon, but slightly inside. And then this energy dependence, if you like, of the lingering horizon. And that's all. And that is why now I'm pretty convinced that it's okay, the first calculation, because we get now exactly the same temperature. Of course, the volume will in principle give you more because it's not just a local thing. But I agree with you. I mean, but I think that if you look at this paper by Walter Moretti, I think it's cited in the last paper that we wrote, or even in the published version of the other one, the Contest Rendus, the one for in honor of the first one.
Any other questions? Okay, now let's thank Stefano again.